One way to get the product rule is to use this rectangle method, and I like this method best because it's a very interesting way of thinking about the product rule. It's probably a way that most people would not think of. So here's a product rule up here. Derivative of f times g of x is equal to f of x derivative of g of x plus g of x derivative of f of x. So in order to get this product rule, I have a rectangle, and it's divided up into u, v, delta u, delta v. So this rectangle here is u times v, and this whole rectangle would be u plus delta u multiplied by v times delta v. And u is f of x, delta u is f of x plus change in x, v is g of x, and delta v is g of x plus change in x. So what I'm looking for is what the two derivatives of this are multiplied together, the derivative of u and the derivative of v. So what I'm going to need as far as this rectangle is concerned, I'm going to need to get delta u times delta v. And I'm not looking for this, and I'll explain why later on, but what I'm looking for is just delta u times delta v. So I can treat it as a rectangle. So I'm going to say delta and then I can multiply these two sides together. So u plus delta u times v plus delta v. And since I only want this part of my rectangle, and just don't worry about this part for a second, I'm going to subtract this area of of this total rectangle minus vu. So when I multiply this out, I'll get u times v, and that is being subtracted up here, so this will cancel out. And what else will I get? I will get u times delta v plus v times delta u, and then I will get delta u delta v. I didn't really need to multiply that out, because since I know I just subtracted out this area of the triangle, I can easily just see that this is delta u times v, and this is delta v times u. Those are on there, and then delta u delta v. So continuing on, now what I'm looking for is the rate of change. So I'm going to have to divide out by delta x, because that's what I'm going to be taking my derivative of in relation to x. And then I'm going to need to find out what happens when it goes to 0. So I'm going to divide everything by delta x. So delta uv And since I'm interested in the derivative, then I need to take the limit of delta x as it goes to 0. So this is what it's going to look like. Maybe I should have just done this in the first place. Oh well, it's too late. Forgot what I was doing. Yeah, this is taking unnecessarily long. So what this is doing is just finding the limit, or just the instantaneous rate of change of the direction of the rectangle moving this way and that way. So this will simplify to d dx of uv, and this u will be pulled out in front. My v's and u's almost look the same. And this final term was a little bit tricky because this is delta u times delta v in relation to x, and this whole term is going to go to 0. And when I was looking in the book, sometimes it just didn't really explain it very well. It's like, oh, it just goes to 0, but I'm not quite sure if this is. It just doesn't really explain it, but from what I can see, this almost looks like an acceleration term, as it's the change in u and multiplied by the change in v. So it's almost like a thisward direction. So if this goes to 0 this way, and this goes to 0 this way, the change in u and the change in v are going to become very, very, very small. So it'll be like 1.01, and then 0.001, and then 0.0001. And when you have two small numbers multiply, if you have a really small number times a really small number, then you get a really, really small number. So this term will go to 0. And I also thought it was interesting because this is, if you think about the rates of change as a rectangle, this linear direction, this direction this way, is almost like the velocity, and this diagonal direction would be kind of like the acceleration. So if this had a separate rate of change, then that would be the rate of change of the rate of change, which would be the acceleration. So I think that's why it is 0, although I haven't really been able to find a good explanation anywhere of why it is, but that would be my best. I'll be my best guess, but I'm pretty sure it would be right. So this term, since it seems to be an acceleration term, and it will definitely go to 0, since these two numbers are going to become closer and closer to 0, they're going to become smaller and smaller and smaller, this net effect will be almost 0. So when I have the derivative, I'm only looking at let's just say I just took a very small x this way, and a very small x this way. Then this would only go very tiny. It's almost like it's just a tiny little corner. So as it goes this way, it just goes to basically nothing. And when I'm only the smallest little unit out here and the smallest little unit out here, this is basically almost nothing. It's just a tiny corner. So I don't even need to put anything here, since it doesn't really affect what I'm doing. So after I get over this part, it's going to 0, then I'm left with something that looks very familiar, and this is the product rule. If I have the derivative of u and v, then I get u delta, or derivative of v, derivative of u. And if I go back up and do my substitutions, u is f of x, g is f of x, so I'll get this product rule right here. I'll double check this whole acceleration theory. I'm pretty sure that, I mean, that just looks like it should be right, but you never know. I didn't really have time to go buy another book or anything like that. I have two calculus books, and neither of them really says anything. Maybe it's just really really obvious to everyone else and not me. But that's my guess. If I find out it's something different, I'll come back and change it. But because that'll be something that I'll always keep an eye out for. I think this rectangle idea is pretty cool.